neural network is not a plus, but a effective way to lose the interest of the audience because everybody knows it. So I promise you guys, I'm not going to add more evidence to the success of big data and this computational paradigm. Especially for speech coding, we're talking about this scenario for the hardware on-device application where the computational resource is at a premium. So we cannot really afford a very large model. That's why we're talking about efficient, scalable solutions with neural network. Okay. I guess most of you have already worked on speech coding, audio coding for years. For some of you, maybe for decades. Just to make my presentation self-contained, I still want to use one slide to introduce speech coding from a very high level. Let's say right now I'm speaking and the signal is transmitted to the listener side, whether in Seattle or in Germany. And the listener, you can make sense of the talk. But the speech itself is not directly sent through the internet. It will be first compressed into this bitstream, which is transmitted to the other side. The decoder will take the bitstream and reconstruct the speech signal. The hope is to achieve as much compression as possible. At the same time, we also want the decoded signal to be perceptually similar to the reference signal. Let's say the sample rate is 16 kHz, which means for each second there will be 16,000 samples to represent a signal. If each sample is represented by a 16-bit fixed point, that means the bit rate is approximately to be 256 kbps. That's a very large bit rate. Usually with a advanced codec, we could bring down the number to 24 or even 9 kbps. Let me play some audio samples. I know it's not a perfect way to do this, but you see my point. I mean, even at 9 kbps, a very great compression, we may not feel the difference. I mean, for 9 kbps you could, but for 24 kbps, the quality is almost transparent.
Iguanas and alligators are tropical reptiles. Iguanas and alligators are tropical reptiles.
A non-contributory plan usually won't pay off for the worker until he retires. A non-contributory plan usually won't pay off for the worker until he retires.
So the design of this codec is not an easy task because we have to make many trade-offs to make this happen. A good codec is expected to be scalable. We don't want a codec that can only function at a specific setting. For instance, when we don't have enough computational resource, it should perform reasonably well at, for example, 9 kbps. But given more resources, the performance should be correspondingly increased. That's the scalability. Of course, lightweight. When we talk about edge applications, if the model is too big, it just cannot be handled by the hardware. This is, people do use deep learning for speech coding. For instance, a WaveNet-based model is one of the methodologies. But the model itself is just too large. It has more than 20 million parameters, which is usually not feasible. Of course, we can conduct network compression or some other techniques to make it smaller, or we can even use an integer to represent each model weight. Still, why don't we start from a simpler model topology? So our work here is to not further push the capacity of neural network. We've seen that, and I personally don't have the intention to do so. Our methodology is to bridge the gap between this conventional DSP methods and deep learning as a modern computational paradigm to make these new models more efficient. This is not really a straightforward way because there are multiple challenges. For instance, if we use a neural network to compress something, maybe an autoencoder is a default answer as the first step. But as you know, this is not sufficient because the bit rate is a multi-product, is the product between two items. The first one is the amount of samples to be transmitted per second. The second item is the amount of B to represent each sample. With this autoencoder, so autoencoder is this type of neural network which tries to reconstruct the input. Because of this middle layer, this very narrow bottleneck in the middle, it can learn a compact representation of the input. However, it could reduce the size of the feature map or the first item here, the amount of samples per second. But each feature is still represented by a 16-bit fixed point. So it doesn't benefit the bit depth reduction. That's why only using an autoencoder is not sufficient for speech coding or audio coding here. If only we could, for instance, use 1 out of 32 kernels to represent each feature. In that case, it's sufficient to just use 5 bits instead of 16 to represent each sample. I mean, we have to include quantization to make this neural network work. This is one challenge, how to make an autoencoder neural codec. Another challenge is that when we talk about end-to-end speech coding, the network learns everything from scratch. This is not an efficient way to model speech because we know that according to source filter model, a speech generation process includes sources and filter. If only we could outsource certain subproblem to an efficient conventional algorithm, maybe we don't need a very large neural network to deal with the rest part. But how to do so is still an open problem. By the way, I really think this is end-to-end is a trending term, but it also can be an abuse of DNN because for speech coding, as you will see later, we don't really have to start from scratch. The third challenge is the discrepancy between the loss function and the actual measure used by human listeners to evaluate the sound quality. When we train a network, we have to resort to some type of objective functions like mean square error or things like that. But eventually, the decoded samples are measured by a PESQ, or for audio samples, we need to find human listeners to collect subjective scores. If we use a suboptimal loss function to train the model, usually the model is not efficient enough to compress the data. So in this presentation, I will start from a trainable quantization scheme that can convert an autoencoder to a neural codec. From there, I want to talk about cascaded cross-module residual learning scheme to achieve scalability without making the model go deeper. Then I will introduce a concept called collaborative quantization, where we borrow a highly mature technique from DSP to make the model even more efficient with even better quality performance. Last, I will talk about a better loss function for audio coding, where we employ psychoacoustic calibration to train the model. Let's start from the quantization part. Let's say now we have this output from an encoder, which is vector H. The hope or the goal here is to map each value in H to one kernel in this kernel vector B transpose. To do that, let's first calculate this pointwise distance, which gives me the matrix D. Usually, with this softmax function, D can be transformed into a probability matrix A. It could be much easier if I could use the pointer here. I'm not sure if I can see where the pointer is, but let me try one more time. Okay, here. Let's take a look at this value, 0.2. Right. This is corresponding to the second row here. The hope is to pick the one with the highest probability here, which means 0.1 in this kernel vector. That means eventually 0.2 will be replaced by 0.1 in this kernel vector during quantization. So there are multiple transformations here. We first calculate the pointwise distance, which gives me the matrix D. With softmax function, D becomes a probability matrix A. If I multiply this D by a negative scalar alpha, then we could simply pick the one with the largest probability here. Of course, to make this happen, this matrix A will need to be binarized. So that if I multiply A hard with B, we're picking the corresponding kernel in this B transpose vector. So if I'm interested in 0.2 here, eventually if the A hard matrix is this, for the second row, only one value is with the probability of 1, and the others are with the probability of 0. So this value 0.1 will be selected. Now, the problem of this operation is that it's not differentiable. If I include the operation like this into model training procedure, that propagation algorithm will be disabled. One way to get around this is to stick to a soft version of A during model training only. In this case, this value is not one and unique kernel in B transpose, but a mixture of all these 4 kernels. At the test time, we will convert this A soft matrix to the corresponding A hard matrix to make sure the quantization is conducted. You may wonder, will the performance drop a lot at the test time if you replace A soft by A hard? Yes, that's why there's another maneuver. Long story short, if we could make this soft version as close to the hard version as possible, at the test time, the performance drop will be minimized. One way to do so is to try, is to increase the absolute value of this scalar alpha. As you can see, if the alpha is -1, the probability is this. If I choose the one with the probability 0.31 over 0.26, it is correct, but the model is confused. It's not so deterministic when it makes the decision. But if I try a larger alpha in terms of the absolute value, you can see that the greatest probability becomes even larger, while the others are getting closer to 0. In practice, you could start by setting the alpha to be -100 or even -300, so that for each row, there will be one value that is almost 1, and the others are almost 0. Okay, so this is the introduction about the scalar quantization. Remember, this is trainable because the B transpose is a variable in your neural network. And your encoder will also be optimized to generate this H vector, this output that can be favored by your quantizer. If I place this quantizer into that autoencoder, this can be a neural codec. During encoding, the size of the feature map is reduced. During quantization, we could also reduce the bit depth. So both two items that are related to the bit rate can be reduced. That's how we reduce the bit rate. I want to add one more thing. This quantizer can be coupled with entropy coding as well. Remember, if we have 32 kernels, it's sufficient to use 5 beats to represent each sample. But if you try Huffman coding on top of that, the average beat can be even smaller to represent each sample. And the decoder usually is another part of the neural network with a mirror topology. This solution is end-to-end. The input is just the waveform of the speech, and the model is trained to recover the waveform. This is a very straightforward way. Actually, if we implement this concept in convolutional neural network, the design can be compact. It only contains 0.45 million parameters. One of the topologies can be this. Let's say each frame contains 512 samples. The input will go through some ResNet blocks, followed by a downsampling CNN layer by setting the stride value to be 2. This is where we reduce the size of the feature map. This is followed by 2 more ResNet blocks. Eventually, we have the code vector. This is where the quantization kicks in, the one that I just introduced, followed by Huffman coding to give the bit stream. The bit stream is transmitted to the other side where the decoder recovers the input. And there, if you calculate the loss, you could update the parameters in between to optimize the problem. This is a very straightforward design by using an autoencoder and a trainable quantizer. The topology is also summarized in this table. I don't want to go through the details of the table, but from this table, you could calculate the total amount of parameters for that network, which is about 0.45 million. It's still much, much bigger than a conventional DSP-based codec, but when we're talking about deep learning, this is one tiny model. Because of the usage of ResNet, we could, well, the original model like this has 1.6 million parameters. Because of ResNet, we could bring the number down to 0.45. So I guess so far, you're already familiarized with the idea of using a trainable quantizer and straightforward CNN-based neural autoencoder to make a codec. Now, the question is, what if the hardware can handle a larger model? Say it can support 0.9 million parameters, not 0.45. How can we achieve a better performance or scalability here? The default way is to enlarge the kernel or making the model go deeper, which is not fun. We have a better solution, which is called cross-module residual learning. I will just use this diagram to illustrate the data flow as I just talked about. The input is X. It goes through the encoder and the code layer, which gives me the code vector H, and the decoder predicts the input. From there, we don't make the model larger and deeper. We just stack another autoencoder with the same topology. The second autoencoder takes the residual as the input. The residual means what is not reconstructed from the first autoencoder. So the input of the first autoencoder is X, and the prediction is X hat. The input of the second one is this, which is the residual part. We could stack even more, so on and so forth. Let me do this one more time. We start by first autoencoder, make the prediction, calculate the loss to update the parameters only for the first autoencoder, and then the second one with its own loss term. And we could also conduct a optimization just for the second autoencoder. Eventually, the prediction will be the sum of the output from all autoencoders. And during fine-tuning, we could use this loss to update all parameters simultaneously. We compared the SNR and the PESQ for the validation dataset. I will just tell you this. For our CMRL model, it has 2 autoencoders, which means there are 0.9 million parameters. This is compared against a single model, which is with a similar topology, but just larger kernels and everything, which gives about 1.6 million parameters. In both SNR and PESQ, CMRL has better numbers. The major observation here is that the solution, or CMRL, can organize a bunch of lightweight autoencoders that can outperform a big autoencoder, even with the combined complexity. The idea is really not new. Conventionally, people refer to this concept as multistage vector quantization. But we bring this concept to deep learning and show that this could achieve a higher model efficiency. For instance, if your hardware cannot handle a gigantic neural network, if we could decompose a big one into several smaller ones with CMRL, maybe we don't even need that amount of parameters to achieve even better performance. That is the first part of the talk. I combined the soft-to-hard quantization with this conventional concept, multi-state vector quantization, into this CMRL concept. The method here is still based on end-to-end speech coding methodology. This is not optimal because, like I said at the beginning of the talk, we don't have to model everything from scratch. That brings me to the third topic of the presentation, collaborative quantization. I really like the way don't throw DSP out with the bathwater. So in this source filter model, the speech production process contains multiple sources and filter. The glottal airflow is being filtered by the mouth and before being generated from the lips. It's not known exactly how to use a computational model for the sources, but we do know that the response of the vocal tract, the filter, can be efficiently modeled by a conventional DSP algorithm. Here in this figure, the response of the vocal tract is just the spectral envelope. That algorithm is called LPC, linear predictive coding. With this Leveson-Durbin algorithm, we could learn this envelope with very few amount of beats. Usually 1 or 2 kbps will be sufficient for this task. Of course, the estimation is not perfect. It's okay. The error is called LPC residual. We could use more powerful models to deal with that part. This is not new again, because usually for a codec, it uses LPC as a preprocessor, and for the residual part, depending on the scenario, it could be a vocoder, it could be a lossless coding algorithm. Of course, here we're focusing on waveform coding. So we argue we could just place our CMRL model here to estimate the residual. And the estimated residual will be used along with the LPC coefficients to synthesize the speech. And this is, how to say, this method is not really sophisticated enough, because that means we simply shoehorn LPC to a neural network. We just follow the LPC algorithm from the shelf, say from AMR wideband to CMRL. The LPC part is a deterministic algorithm. So there's no interaction between LPC and CMRL. The goal for collaborative quantization here is to make LPC a trainable block in CMRL. Why do we have to do so? Think about this. If we assign too many beats to the LPC part, the residual will be very soft and noisy, because the goal for LPC algorithm is to minimize the energy of the residual signal. Another edge case is when we don't locate any beat to LPC. In that case, it's just an end-to-end solution, because that's where we model everything from scratch. Between these two edges, maybe there's a sweet spot. To find that sweet spot, we have to make these two parts interactive with each other. That's why we propose collaborative quantization. If the LPC part is trainable, it can decompose the input into the residual and the coefficient. The residual will be the input of the neural network, and the estimated residual along with the coefficients will be used to generate the reconstructed speech. If I zoom in this part, I want to illustrate why this LPC analyzer can be a trainable component. Again, the input will go through high-pass filter, pre-emphasis filter as usual, and we use Levinson-Derming algorithm to calculate the coefficient. Here, the quantizer for the coefficient is soft-to-hard quantization. Remember, that part is trainable. So if we combine this trainable LPC analyzer with CMRL, by setting target bit rate, for instance, 24 kbps, the model can find the right amount of beats to be allocated to LPC, and the rest part for quantizing the residual. This is achieved by collaborative quantization. In fact, in the PESQ score, we could see that CQ has a noticeable margin against LPC CMRL, where we just add LPC as a deterministic preprocessor to the neural network. You see from here, the PESQ score is hugely improved for 9 kbps and 6 kbps, 16 kbps. Although in terms of the PESQ score, they're not as good as Opus. However, in a Mushra test, at 24 kbps, both CQ and LPC CMRL outperform Opus at the same bitrate setting. Although at 9 kbps, the LPC CMRL model is not as good as AMR wideband. CQ is kind of in a par with AMR wideband. Again, I need to emphasize this. Our goal is to not really outperform this conventional codecs with a large margin, because we intentionally choose a very compact neural network to for this problem. comparing with WaveNet and its own predecessor, KNet, CMRL only has 0.9 million parameters, so it's a tiny neural network. Let me play some audio samples here.
Iguanas and alligators are tropical reptiles. Iguanas and alligators are tropical reptiles. Iguanas and alligators are tropical reptiles.
I guess the reason why the listeners are in favor of our model is because the decoded sample from Opus sounds a little bit muffled because the energy at high frequencies are kind of lost. But at 24 kbps, I guess they all perform very good, and I don't think we could tell the difference without a good headset. Let's see.
A non-contributory plan usually won't pay off for the worker until he retires. A non-contributory plan usually won't pay off for the worker until he retires. A non-contributory plan usually won't pay off for the worker until he retires. A non-contributory plan usually won't pay off for the worker until he retires. A non-contributory plan usually won't pay off for the worker until he retires.
Yeah, it's just, for me, it's just hard to tell. I guess it can be even worse for the listener side, given that this signal will also be compressed and then decoded. Anyway, so far we've talked about two of our previous work, CMRL and CPU, collaborative quantization, that brings a conventional LPC algorithm into a neural codec. Let's move on to the last section of the presentation. Here, I extend the neural codec to audio signals. Because for speech, there have been effort to implement a story like loss function or task like loss function. But for audio quality, I don't know if there is a good objective measure that is equivalent to human auditory perception. For instance, if I employ the previous neural codec directly to audio coding, the performance is far from satisfactory. Actually, I recorded this audio clip by myself in a studio because I don't want to offend the singer if I mess up the audio quality. So I performed by myself. This is at 168 kbps, which is a relatively high bitrate setting, but the loss function is just based on mean square error. It's just not perceptually salient enough. As you will see, the performance is not good.
一看花水中望月，飘来又复去。一看花水中望月，飘来又复去。
We have this decoded samples online, but I hope that you already figured out that the decoded sample from CMRL is not comparable for now.
一看花水中
Sorry. That's where we resort to psychoacoustics because traditionally it helps many audio codecs, such as MP3, to achieve coding efficiency. Basically, not all sound is treated equal by our human ears. Say some sounds are too soft at certain frequency, so it's inaudible, even though the sound does exist. So this one is inaudible. I guess this one is still audible though. Given a certain frequency, the loudness of the sound will determine if the sound itself can be audible or not. If I play two tones together, Sometimes you could tell, yeah, there are two tones, but sometimes when the frequency of these two tones are too close together, the interfering beep is masked by the major tone. Your ear will barely distinguish one tone from the other. Let's see. I guess you could tell that there are two tones, but let me see. Yes, there are two tones. Not sure. I guess some people will say there's only one tone. If I visualize the spectrogram, I can see that if this frequency of this interfering beep is very close to the major tone, it will be masked by that tone. This masking effect is studied in psychoacoustics. Basically, if the tone is too soft at a certain frequency, it can be inaudible. If the tone right next to a loud tone is also kind of soft, it will also be masked. In audio coding, what I mean is this: for this tone, we don't have to assign too many beats because it's masked. Of course, this can lead to some quantization error or this artifact. As long as the artifact is also masked by this curve, we're good. It won't really hurt the subjective experience. Inspired by this psychoacoustics, we implement the psychoacoustic model in Python. The model detects the tonal masker and the noise maskers, the corresponding masking curves, along with the absolute hearing threshold, which is this red dashed line. We could get a global masking threshold, which is this red hard line. With this global masking threshold, long story short, we could inform the model to pay more attention at certain frequency beings while being easy otherwise. So the beats are allocated in a wiser way. Now, if I play the reference again. And even at a lower bitrate case, 112 kbps. So this is near transparent according to the subjective score collected from Mushra test. So sorry. Anyway, the difference is also explained in these two figures. The power spectrum of this artifact, the power spectral density of the artifact is well below the global masking threshold, which explains why the artifact is less inaudible, less audible in this new model. I'm not sure, but I tried to make this presentation align well with some ongoing project in the group, in the company, but I don't know if I can do that. I do know that at Microsoft, people consider input from multiple modalities. Even for speech, we have ASR model and some other models for speech enhancement and stuff. These models are already implemented in deep neural network. I'm not sure what's going on for coding, but if a coding algorithm is also implemented in this related method, at least we could fine-tune all these components simultaneously, hopefully to achieve a better global solution, although I have no concrete clue that this would be a plausible assumption. But yeah, this is my presentation. I remember the goal is to bridge the gap in between to improve the model efficiency for edge applications. Thank you.
Great, very interesting talk. So, questions? No questions? Then I'll start with a question. So going back to your the network that tried to learn a linear prediction, was that really a linear function that you tried to learn, or was it also could it also be a nonlinear function, and would that make sense in that context?
Yes, I probably should have clarified that a little bit more. Right now, when I say the LPC part is trainable, only the quantization part is trainable. I didn't really change any other components here. The high pass filter, the preemphasis filter, they are just borrowed from MR wideband.
Mm-hmm.
So I think it's just a linear model, if I understand that correctly.
And so what did your network predict? And did it predict kind of the linear prediction filter, or did it simply output like the residual or something like this?
Right. Yes. The output of the CMRL is the LPC residual. The residual, which is this very soft, very soft wave in orange color. This, along with the coefficients, will be used to synthesize the speech. So the output of the CMRL part is the residual.
Mm-hmm.
To be frank, quantizing the residual is even more challenging because I guess the structure for this noisy residual is much harder to be learned as opposed to the raw PCM waveform. So if I calculate the SNR, it's much lower. But when we synthesize the speech, although the passive score is also lower, it just sounds better. So that's why you could tell that there's a discrepancy between the comparison in terms of the PESQ and the comparison in terms of the subjective score. The passive score is not as good, but listeners are in favor of our model.
Thanks. More questions? No?
I have some questions on the training on the CMRL. Yes, I'm just curious to know, so have you tried to train end-to-end? Maybe potentially we might have the learning rate for the deeper layers. So I'm just curious, have you tried to train all these networks end-to-end?
Yes, first, this CMRL is trained in an end-to-end setting. Second, you are right. The learning rate for the second and the rest autoencoders is much smaller than the one for the first autoencoder. And it's even smaller during fine-tuning. For instance, if the learning rate is 1e minus 3 for the first one, you could use 1e minus 4 for the second one, and 1e minus 5 for the fine-tuning, because when during fine-tuning, these parameters are already initialized in a decent way. If it's tuned with a very large parameter, the system can be collapsed, or it's not stable. That's why empirically we chose a much smaller learning rate.
sorry, I might miss something. So I joined the meeting in the middle. So when you train the second module, for example, did you freeze the parameters on the first module, or you just change the running rate?
When I optimize the second autoencoder, the first one is freezed. There are 2 rounds. The first round conducts a greedy training scheme. So I take turns to train each of the autoencoder from left to right. During the second round, we conduct fine-tuning, where all parameters are updated simultaneously.
Okay, thanks.
Right. More questions? Then I have another one.
Okay.
You talked about this integrating this psychoacoustic model and the end. And this was all kind of, there was no training involved, right? That was all basically a hard-coded model. So did you have any ideas if there would be a possibility to kind of learn such psychoacoustic effects in a neural network model?
Yes, actually, I thought about that, although this is just a highly immature idea. So first, the calculation of this global masking threshold is deterministic, but it is integrated in model training. So there are some loss terms to liberate this. But can we really learn this masking curve? I think there is a topology called a clone network. And there is a learning mechanism which is called self-supervised learning. So let's say if the input are samples decoded from different codecs, opus, if we could a hidden representation from this clone network, input are different because they are from different codecs, the hidden representation should be equivalent because perceptually they sound almost perfect. I'm not sure if that makes sense to you. Let me put it in another way. So if we could define a distance or a loss in a hidden space from a clone network, maybe that could be comparable to this psychoacoustic curve. I guess. Yes, it's not a mature idea, but I thought about that a few days ago. Yeah.
Yeah. Yeah, that's kind of an interesting thing. So it could also be something like with reinforcement learning, but it's probably a very difficult problem because you can only get, in the end, you want to get feedback from humans, right? If you want to adapt those masking thresholds online, for example, but it's probably a very tricky problem to solve, but
yeah,
could be something to think about.
Right. Appreciate your feedback.
Great. More questions?
Yeah, let me see if I include my email there. But if you later find any question you want to ask me, feel free to send me an email. I'll be more than happy to answer the question.
Mm-hmm. Yeah, I really enjoyed the talk. It's really nice to see someone not building larger networks, but actually trying to increase the efficiency and that's actually getting more and more important, and as also these networks become more practical and more tractable to be used in edge devices and stuff like this. So yeah, really, really interesting work and nice perspectives. So if there are no other questions, I think I'll stop the recording. How do I do that? And